So this video is going to look at what we call Hess's law and then finish up with bomb calorimetry. So Hess's law is another way that you can find a delta H. So from our previous discussions, we were just doing heat of formation in the previous video. So that's one way you could find the delta H. Another way is to do the chemical reaction and find your Q, and you could do it that way. And the third way is what we call Hess's law. So note that the change in enthalpy of individual reactions can be added, okay? So I could take individual reactions and the overall delta H, and I can manipulate them to get to a new equation. So I'm going to take this as a reaction 1 and reaction 2. And I'm trying to get it so that carbon in the graphite form plus oxygen goes to carbon dioxide. So can I manipulate these two equations to get to there? And then I could just add my delta H's. So just note that if you are flipping a reaction, meaning changing from the reactant, shifting it to the product side, and the product's coming over here, you're going to change the sign, because if it is exothermic, it's going to become endothermic. If it's endothermic, it's going to become exothermic. And if you are multiplying a reaction by a factor, you're going to multiply the same factor by the delta H. So if I'm doubling the reaction because I need to cancel things out, then I'm going to double the delta H. So those are the essentially the rules. So I'm going to rewrite the equation down here. So I'm going to pause the video and then come back. So what I did was I took the first reaction and just wrote it as it was. I noticed that in this reaction, what I want is graphite on the reactant side. So that is where it is on this. So I just kept it as is. And then the second reaction, I noticed that I needed CO2 on the product side. So I flipped it. Okay, so I flipped the second reaction. So when I flipped it, it becomes negative 283. And the CO and the 1/2 oxygen go on the left, and the CO2 go on the right. And that's perfectly acceptable. So then I'm going to take both of these reactions and add them together. So I end up with graphite carbon, okay? I end up with the COs cancel each other. I have a full 1 mole of oxygen, and I'm left with CO2, okay? So now all I have to do is add the delta H's, and I end up with negative 393.5 kilojoules. So for this reaction, that's my delta H. So where this is useful is some of these reactions are not very easily accessible. Maybe you can't get graphite. Maybe it's too dangerous to do it. Many different reasons. So that is why it is another way we could do a delta H. So the second problem that I have on this page, I want you to find C graphite plus hydrogen goes to methane. So you're going to actually use this equation with these other two equations to find that equation. So I'd like you to pause the video and see if you could find the answer. When you come back, you're going to see my answer. All right, so I took the equation we just solved for and put that here, and I kept this graphite on the left because that's where I want it on my final reaction. I took the second or third, whatever you want to call it, the CH4 needs to be on the product side, so I flipped that reaction so the negative 890 became 890 over here. And then this one up here, I needed to have 2 hydrogens. So what I did was I doubled this top reaction. So I have 2H2 plus O2 goes to 2H2O. And then I have to double my delta H in, so it becomes negative 571.8. So then I probably have everything I need here. So I want to cancel things out to make sure that I have everything. So I have 2 waters, those are gone. I got a CO2, that's gone. I got 2 oxygens on both sets of sides, so I'm left with C graphite plus 2H2 goes to CH4, okay? So then all I have to do is add up the delta H's, negative 393, the 890, and then the negative 571. So the delta H of this particular reaction is negative 74.9 kilojoules. Okay, so again, it's just another tool we have in our toolbox of finding a delta H. So what I want to finish up with is what we call bomb calorimetry. And this is kind of like a side conversation. Used to have a more involved discussion of this, but instead we're focusing on just calorimetry and what we call constant pressures, pressure situations rather than what we call constant volume. So this is called a bomb calorimeter, and yeah, it sounds exciting, but really this is how you can have a chemical reaction taking place where a volume is kept constant. So if a gas is being produced, it's actually not allowed to leave the system. So this is a bomb calorimeter, and I will have a video up so you could see it live and in person. But this is how we get our food calories, okay? So if we have Cheetos and we eat Cheetos and we look in the back of the packaging, it has a certain amount of calories for how many grams of Cheetos. Well, how they determine that is putting it into a bomb calorimeter. So you put a small sample into here, and then what you do is you have a way to ignite it and you pump in oxygen. So what you are doing is a combustion reaction, okay? So this is a combustion reaction. And combustion reactions are going to be a carbon molecule plus oxygen is going to produce carbon dioxide and water, okay? So when you burn it in a bomb calorimeter, it burns what we call clean, meaning you have just CO2 and water. So all of the carbon in that item has been completely used up. And the oxygen is always in what we call excess because you are pumping it in. So what do you have on the outside here is water. Okay, and so when this burns and it generates energy and the heat comes out, the water changes temperature, and you could then calculate how much energy was given off when that combustion reaction took place. So in this, you do have to consider that the calorimeter is going to have some component to this whole thing. So the system itself is the calorimeter and the reaction taking place. So because this is under constant volume, okay, we set the system to 0. So that means the calorimeter itself is going to be essentially what the reaction is. So this is a way for chemists and other scientists use this to determine essentially all of those heat of formations that we have been talking about. So this is a way to actually calculate that. So if you have a standard bomb calorimeter and you know how much the temperature went up, you then know essentially what the heat of the reaction is going to be because all of the energy is going into the water. So then you could figure that out. And again, if it has to pull energy from the water, the temperature will go down. And if it's exceeding or heating up the water because it's losing energy, you will see that. But we are assuming, and this is true, all combustion reactions are exothermic. So they will all see a change in temperature going up.